Hello guys, my name is Abdulrahman Mahmed Awad. On today's episode, we are going to look into physiology and our topic is going to be erythropoiesis. If you are new to this channel, kindly subscribe to our channel and check the description below for our previous videos. Erythropoiesis, of course, is a very common topic in the basic medical sciences, especially among the 200 level students. Before moving on, we all know what erythropoiesis. Some of us already have idea about erythropoiesis, but during the course of this lecture, we are going to talk on the morphology of red blood cells. Now, let's look into the morphology of red blood cells. Red blood cells. The term morphology, it means you are trying to describe the gross appearance of that particular subject matter. And here we have red blood cells. So under the morphology of red blood cells, we are going to look into the different properties of red blood cells. It could be functional property, the shape and the size. We're also going to look into the structural property. Let's go to our whiteboard and see what we can do in terms of illustrations and explanation and clarification. Now, this is our whiteboard. Now, talking about the size and the shape of red blood cell. The shape of red blood cell is biconcave in shape, and this is what it means. Okay, it is biconcave in shape. So if we look at this cross-sectional, drawing of red blood cell, you are going to see the biconcave shape of red blood cell. The periphery is more thicker compared with the center. So the center is thinner. So, and one thing about physiology, like I do always say, is that in physiology, you play around with figures, you play around with values, okay? And these values occur in ranges, and also depending on the text that you normally use to study, so the values might change depending on the text. But then just know that physiological values occurs in ranges. So we are going to look at some values here. So if we check the total length of the red blood cell, the total length of red blood cell is about 7.8 micrometer. Okay, it's about 7.8 micrometer. Now, let's look at the diameter. This is the total diameter, okay? 7.8 micrometer is the total diameter. Now, let's look at the length or the diameter at the thickest periphery point. So this is the periphery. So around this place, the length is about 2.5 micrometer, okay? 2.5 micrometer, okay? But then when you move down to the center, you notice this place is the thinnest point. So at the thinnest point, the size is about less than or equals to 1 micrometer, okay? At the thinnest point. Now, the biconcave shape or the biconcave nature of red blood cell confers so many advantages to red blood cell erythrocyte. Okay, one of such is that this biconcave shape ensures that whenever the red blood cell is passing through the circulation, is passing through the capillary, the blood vessels, it can change form. Okay, it can change forms. Now, I said the total diameter of red blood cell is about 7.8 micrometer. However, when in some capillaries, in some blood capillaries, the total diameter could be as low, especially in the capillary network of the spleen. Okay, so the capillary diameter could be as low as 3 micrometer. Now, how do you then expect red blood cell that has a diameter of 7.8 micrometer to fit and pass through this vascular lumen, through this capillary lumen, which is about 3 micrometer? So that's where the concept of the red blood cell can deform like this, can deform to pass through. So this deformity, these changes in shape just to pass through the capillaries is one of the advantage of the red blood cell being biconcave shape. Okay, so the biconcave shape of red blood cell confer such advantage. So another advantage which we need to look into is the fact that this biconcave shape also increases the surface area of the red blood cell for easy diffusion of oxygen and also for easy and rapid diffusion of oxygen. Okay, so we are going to later look into the constituent of the red blood cell, what it contains. Okay, but then let's finish what we are saying about the shape. About the shape, yes, biconcave shape. So these are the advantages, and also this biconcave shape also allows the cell membrane to be in excess. So the cell membrane is in excess. If at all at any point in time there is a need for the red blood cell to to add to its normal constituent. Normally the red blood cell contains hemoglobin, oxygen. There are no organelles. There's no nucleus. Okay, and there is no nucleus, but then it contains hemoglobin, oxygen, and some cytoplasmic enzymes. Okay, so if at all there's any need for an increase in the constituent of the red blood cell, there's already an excess membrane, so that allows the red blood cell to also to modify in response to the increase in the constituent of a red blood cell. Okay, so that is the importance of the biconcave shape of a red blood cell. So now, in some pathological processes, this biconcave shape can assume different shapes. It can be spherical, and this is known as spherocyte. Spherocyte. This is known as spherocyte, as seen in hereditary spherocytosis. When we won't be discussing about spherocytosis in this lecture. It's actually beyond the scope of this lecture because that's actually hematology. But then you should also know that variation can occur, and that is what morphology is all about. So even when asked in exam to discuss about morphology, we discuss morphology based on the size, based on the shape, based on the normal structure, based on the functional property. Okay, and you discuss about the variations. Okay, the variations are very, very necessary. So variations are so necessary in physiology, just as we discussed in our previous video where I was saying that variation in body fluids. So I made us to know that the infant, the infant, the children, the elderly, variation in terms of age, that is they have different water constituents. So if you have not watched the video, the link is inside the description below. Kindly check out. So, and I also made mention that okay, variation also exists in terms of sex. So, different constants of water, different volume of intracellular fluid and extracellular fluid in male and female. So, the percentage are different. So now we are talking of variation in terms of the shape. I said some cell can assume spherical shape, spherocyte. So in this type of cell, they can what? They can rupture easily because they won't be able to pass through this 3 micrometer diameter of the capillary, especially the capillary of the spleen. So they easily undergo changes and they rupture easily. So they don't really have long life. They don't really have long lifespan. Okay, spherocytes are seen in spherocytosis, and the test you do to confirm this is the osmotic fragility test. Okay, osmotic fragility test. So as you can see, there's already a tension on the cell membrane. Okay, as you can see, there's a tension on the cell membrane already. So anything that is this red blood cell won't be able to accommodate any more constituents. So anything you are including inside the cells, we just end up causing just end up leading to the rupture of the red blood cell spherocyte. So another variation you should know is elliptocyte. Okay, so it could occur as ellipses. So if it occurs as ellipses, so the red blood cell will not be able to function optimally as well. Another variation in terms of the shape that you should know, elliptocyte is also a variation in terms of shape. Okay, another variation you should know in terms of shape is sickle shaped, such as in sickle cell anemia. So instead of the cell to be biconcave like this, the cell will be sickle shaped. So and you know that in this sickle shaped cell, This cell, whenever this type of cell, the sickle shaped red blood cells are passing through the capillaries, they can end up, they can end up occluding. So they can end up occluding the capillaries. Okay, and that leads to the manifestation of sickle cell anemia. So if there's occlusion in the lungs, so we're talking of what acute pulmonary crisis. If it is occlusion of the blood cells in the bone, the capillaries of the bone around the bone area, you're talking of a bone crisis. Okay, so there will be bone pain. So this sickle shape is just as a result of a mutation in the some of the amino acids, the valine and glutamine, valine being substituted for glutamine in the beta globin chain of the red blood cell. So this is another variation. But however, in some other cases, when we have different shapes altogether, okay, when we have different shapes of red blood cell in the circulation, and that is known as poikilocyte. Let's move to a fresh page. So that is known as poikilocyte. When there is a different shapes of red blood cell in the circulation, that's a poikilocyte. So now let's talk of variation in terms of sizes. Okay, variation in terms of sizes. Now the normal size of a red blood cell, as I've said earlier, is that the diameter is about 7.8 micrometer, and the diameter at the thickest periphery point is about 2.5 micrometer, and the diameter at the thinnest center point is about 1 micrometer or less. Okay, so this is the normal size of a red blood cell. Okay, however, in some cases you could have smaller red blood cell and bigger red blood cell. So when there's variation in sizes could either be on the high side or on the low side. So variation on the low side, that's where we're talking about microsite. Okay, microsite. While the variation on the high side, that's why we're talking about macrosite. Macrosite. Don't mind my handwriting. Macrosite. So microsite means smaller cell, while macrosite means a larger cell. Because the normal so in terms of this size, the normal MCV, mean corpuscular volume of a red blood cell, this mean corpuscular volume is a very important parameter, which of course serves as a measure of it serves as a measure of the average size of red blood cell in circulation. Okay, MCV, mean corpuscular volume, serves as a measure of average size. It serves as a measure of average size of red blood cells. So, and the normal value is about as I've told you, values in physiology do vary. Okay, the normal value is about 80 to 100 femtoliter. Okay, femtoliter. So any size that is less than 80 femtoliter, so you refer that as microsite. While size that are greater than 100 femtoliter, you refer those as a macrosite. Okay, so it's actually an important parameter which of course can be used in to diagnose various diseases. So when we get to the maturation requirement of red blood cell, the vitamin B12, the folic acid being required, so we talk more on this, because whenever there is deficiency of any of this maturation requirement, the cell will not be able to divide. Okay, and when the cells are not dividing, they will occur at their bigger form. Okay, we know about cell division. Okay, bigger cells will divide to form the smaller one. So by the time we are having bigger cells, which are known as megaloblast. Okay, megaloblast. So that of course could lead into macrosite. Okay, macrosite. So the mean corpuscular volume will be greater than 100 femtoliter. So another variation which is the normal is the nomocyte. So I told us we have microcyte, there's macrocyte, and there is nomocyte. So nomocyte is just the normal size of the red blood cells, which of course, as I've told you, is about 80 to 100 femtoliter. That is the normal size. Okay. Now let's look further and talk on, okay, we've talked about the shape, we've talked about the size and the variations that exist in that regard. Now let's look at the normal structure of red blood cell. So for red blood cells has cell membrane. Okay, there's cell membrane, there's no nucleus, and no organelle. No nucleus and no any organelles like rough endoplasmic reticulum, no smooth endoplasmic reticulum, no mitochondria, so no organelle. However, it should be noted that red blood cells has cytoplasmic enzymes. Okay, there are presence of enzymes in the cytoplasm, cytoplasmic enzymes. So there's presence of enzyme in the cytoplasm of red blood cell. And chiefly, this enzyme, the major enzyme in the cytoplasm of red blood cell is the carbonic anhydrase. We are going to talk more on this when we get to the functional property of red blood cell, carbonic anhydrase. Okay, this enzyme is very important in the buffer system or in the acid-base buffer system of the red blood cell. Okay, so moving on. So now ATP is actually generated from glucose. Okay, you know that ATP can also be generated even without in a cell that doesn't have functional mitochondria. So that's no surprise. If I said red blood cell has no organelles, that does not mean they can't make use of glucose to generate, because normally red blood cell has glucose transporter, GLUT. So glucose transporter, in which glucose can come in to form ATP, and this ATP combined with the cellular, combined with the cytoplasmic enzymes ensures that the cell membranes are actually in its correct form to avoid rupturing or to avoid any damage. But then when we get to life cycle and fate of red blood cells, life cycle and fate of red blood cells is also a common question in exam. We also try and talk on if there is exhaustion after some days, of approximately about 120 days, there will be exhaustion of all the cytoplasmic enzyme, exhaustion of the ATP. So in that very case, the pliability of the cell membrane will not be maintained again. And in that very case, whenever the cells enters into smaller capillaries, especially smaller capillaries in the spleen, that's why the spleen is referred to as graveyard of red blood cells, the graveyard, like the cemetery, because by the time a week old aged red blood cell enters into that capillary, the diameter is about 7.8 micrometer, and this aged red blood cell is about to enter into a capillary that's about 3 micrometers. So logically, you should know the outcome of that dangerous adventure. So the moment the red blood cells get into it and cell membrane are not getting enough energy, the cell membrane are already weak. There's no energy. The cytoplasmic enzyme have been exhausted, because of the fact that the red blood cell has become aged. So there's nothing that you expect than what the red blood cell will meet their doom. Okay, that's why it's known as the graveyard of red blood cells. So whatever it is that happens, you are going to know more about it. So now that is just about the normal structure of a red blood cell, and you should know that the volume of red blood cell in the cycle, the normal volume of a red blood cell in the circulation is also about 90 to 95 cubic millimeter. So 90 to 95 cubic milliliter. So the normal volume of a red blood cell is 90 to 95 milliliter. Okay, so this is just the overall volume. This volume is actually different from the mean corpuscular volume. So mean corpuscular volume is actually talking about the red blood cell itself. Okay, so now this is just about the normal structure of our red blood cell. Okay, we soon go back to our slide and see what we have. But before moving on, let us have a solid foundation of what this lecture is all about. Okay, so I believe that will consolidate our understanding, and of course, you know, makes the understanding to be more easier and better. So now let's talk on the concentration. So under the morphology, we've discussed the shape, we've discussed the size, we have discussed the normal structure. So let's discuss about the concentration. So this concentration variation also exists. So variation in terms of sex, male and female. So they have different concentration. So in male, is the concentration of red blood cell in male is about 5.2 million, 5.2 million per cubic milliliter. Okay, 5.2 million per 5.2 million of red blood cell. That is the total number of red blood cell. So per cubic milliliter. Okay, per cubic milliliter. Okay, per cubic milliliter. Sorry about this. This is micro, not cubic. So per cubic milliliter, okay, per millimeter cube, okay. So 5.2 million, 5.2 million per millimeter cube per millimeter cube, okay. So this is the normal concentration in adult male. However, in female, the concentration is about 4.7 million per millimeter cube. Okay, so looking at this has this is not the absolute value. It could be 5.2 million plus or minus 300,000. Okay, so meaning that what the range is about 4.9 million to about 5.5 million, and same thing applies for the female value. The female value, which is 4.7 million per millimeter cube. So there's a range plus or minus 300,000, plus or minus 300,000, which of course is going to give us about 4.4 million to about 5 million per millimeter cube. Okay, so that is variation based on sex. So variation could also exist based on the altitude. So just as we are going to be saying later on about the sensor of erythropoiesis. So there are things that stimulate erythropoiesis, and that is the oxygen tension. So for people living at high altitude, because in high altitude the atmospheric oxygen is very low, so they have is relatively very low. Let me say it that way. So they have increased erythropoietin production. So and when there's increased erythropoietin production, it stimulates erythropoiesis, and there will be more concentration of red blood cell in circulation at that point in time. So for their own value might be more or way greater than 5.2 million. So it could be about 6 million, it could be about 5.8 million or thereabout. So that's another variation based on the altitude. So now let's move on to let's talk about the under the structural component. I think we should also talk about the hemoglobin inside the red blood cell. So I told us that if we have the cell membrane this way, the cell membrane, there are no organelles, no nucleus, no mitochondria, no rough endoplasmic reticulum, no smooth endoplasmic reticulum, no Golgi bodies. Okay, so the cytoplasmic enzymes, of which the main cytoplasmic enzyme is the carbonic anhydrase, and also there's hemoglobin inside the red blood cell. But now, how much of hemoglobin is inside the red blood cell? So this we need to actually talk about it. So the maximum hemoglobin level that can be inside red blood cell is 34 gram, 34 gram per deciliter of cell. Okay, 34 gram per deciliter of cell is the maximum uh, hemoglobin that could be inside the is the maximum hemoglobin that could be inside that red blood cell per deciliter of blood. Okay, so 34 gram. So when you want to play with your values, I say you can play with your value. So if you want to convert this to liter, it will be 340 gram per liter. Okay, it's going to be 340 gram per liter. So this is the maximum. However, this is not the absolute value. The absolute value is that for male and female that has hematocrit level of 40 to 45%, that is the normal hematocrit level, about 40 to 45%. So for a male you have about 15 gram, a male you have about 15 gram, a male you have about 15 gram per milliliter of cells, or deciliter is still the same, 15 gram per milliliter of deciliter of cells, while a female is going to have 14 gram per milliliter or deciliter of cells. Okay, so let's go to another board. So a male you have about 15 gram per milliliter of cell, while for female 14 gram per milliliter of cell. So looking at this carefully, this is the average hemoglobin level, and I told us that the maximum that could be contained per milliliter of cell is 34 gram of hemoglobin per milliliter of cell. That is the maximum. Okay, let's get it right. So inside hemoglobin, of course, when you check the structure of hemoglobin, so there's heme and heme plus globin. There is heme plus globin. Okay, so for the heme, inside the heme is made up of iron plus the pyrroline, the protoporphyrin 9. Okay, iron plus protoporphyrin 9 makes up heme. So, and you know that iron loosely binds to oxygen. Iron loosely binds to oxygen, loosely. Okay, the oxygen does not really form ionic bond with iron because it has to be a reversible binding. So iron loosely binds with oxygen. Now, since you have looked into how much of red blood cell you can have in circulation, I told us the correlation is about 5.2 million per millimeter cube for male, while for female is about 4.7 million per meter cube, plus or minus 300,000 for both sex. So now we've looked at how much of our red blood cells we can have in circulation, and I told us that inside red blood cells there's hemoglobin, and we have also looked into how much of hemoglobin you can have inside red blood cell, which is the maximum is about 34 gram per milliliter of cells. Okay, or you say 150 gram per liter of cells, or you say 140 gram per liter of cells, which is 14 gram per milliliter of cells. Okay, so just about you changing the SI unit of the value. So now we've talked on how much hemoglobin. Now let us, and I said that inside hemoglobin there's oxygen that loosely binds with iron. So because inside hemoglobin is divided into heme, there's heme part and also the globin part. Okay, the globin part is the polypeptide chain that constitute our hemoglobin, and there's also heme part. And I told us that heme part is made up of protoporphyrin 9, which is the pyrrole ring, and iron. So iron loosely binds to oxygen. Now let's look at how much of oxygen we can have inside how much of oxygen there are inside hemoglobin. Okay, so for every 1 gram, per mil of red blood cell of this hemoglobin per mil of cells, per mil of red blood cell, for every 1 gram of hemoglobin per mil of red blood cell, the concentration of oxygen obtainable is about 1.34 mil. 1.34 mil of oxygen. So when you do your calculations right, and you multiply 15 gram by 1.34 mil, you are going to be getting about 20 milliliter of oxygen per 20 milliliter of oxygen per 20 milliliter of oxygen in in about 15 gram of in 15 gram per milliliter of cell. While for female, if you multiply 1.35 ml multiply by 14, you'll be getting 19 ml of oxygen per 14 gram per mil of red blood cell. Okay, so this is just the normal value of oxygen that is necessary. As you know that when we get to the functional property, we'll be explaining that uh red blood cell is responsible for transporting hemoglobin, and you know what hemoglobin transports, which is oxygen. So it's actually responsible for delivery of oxygen to the body tissues. So these are the things you need to know. The concentration of red blood cell in the circulation, 1. Inside the red blood cell, there is hemoglobin. 2. Concentration of hemoglobin inside the red blood cell, you should know it. Then 3. Inside the hemoglobin, there is oxygen. So the concentration of oxygen inside that hemoglobin, you should also know it. So it's more like you are talking layers. The first layer is red blood cell itself, followed by hemoglobin, followed by oxygen. Okay? Now let's look at the functional properties of let's look at the functional property of red blood cell. So in looking at the functional property of red blood cell, just as I've been discussing since, it transport hemoglobin. So the first thing is transport of hemoglobin. Okay, transport of hemoglobin is the first thing. So and you know that hemoglobin transport oxygen. So you can just say it's red blood cells to transport oxygen from the lungs to the tissues. Because at the lung level, at the level of at the pulmonary level, there's exchange, you are inspiring, you are breathing in air, and that air contains oxygen. Okay. So in that very case, the hemoglobin in the pulmonary capillaries, they tends to what? They absorb the oxygen and transport it to different tissues of the body. Okay, so transport of oxygen. So another function you need to know is that I was telling us that when it transports oxygen now to the tissue, so from the tissue, let's say this is the lung. So from the lung to the tissue, transport of oxygen, and also from the tissue to the lung, CO2. So the CO2 has been generated in tissue from cellular respiration when 6,6H12, your glucose, when it combines with water to form 6CO2 plus 6H2O plus ATP, okay, which is adenosine triphosphate, which is the energy that has been generated. Though that CO2 is more like waste product of metabolism, okay, and some of this oxygen can be carried, about 30% of it also can be carried also by the hemoglobin as deoxyhemoglobin to the lungs. Okay, but then the major bulk of oxygen is actually transported in form of bicarbonate. So how does this happen? So now this will lead us to the second function of our hemoglobin, which is cellular enzymatic activity. Okay, so hemoglobin has cytoplasmic enzyme, and of which the major one we should know is the major one you should know is carbonic anhydrase. Carbonic anhydrase. So this carbonic anhydrase helps with the reversible conversion of CO2 to bicarbonate. Okay, so let's go to to another board and see what we can do. So at the tissue level, CO2 is being produced, and I told us where the CO2 is coming from. So CO2 will combine with water, and this reaction is reversible, and it is catalyzed by carbonic anhydrase. Carbonic anhydrase. Okay, so this is going to give us carbonic acid, H2CO3. Okay, and this carbonic acid can also be further worked on to give a proton, to give hydrogen ion plus bicarbonate, HCO3. So this bicarbonate can be carried in the plasma. So some of this bicarbonate can be carried in the plasma. So meaning that what CO2 is carried from the tissue to the lungs in form of bicarbonate inside the plasma. One, I also thought that, of course, some of this CO2 can also go directly to hemoglobin to be carried, but it is just, a little amount of CO2. But the majority of CO2 that is being formed at the tissue level is being carried in form of bicarbonate from the tissue to the lungs. And whenever it gets to the lungs, there could be, so in the lung level, at the lung, there will be a reversible reaction again, of which bicarbonate can combine again with hydrogen ion to give carbonic acid. From there, CO2 and H2 will be the ultimate product. So this reaction can be reversed. And when this reaction is reversed, so the CO2 we have can then be expired out from the lung. So it can then be expired out from the lung. So I hope you get that simple and basic reaction. Okay. So that is just the major function of the major functional property of a red blood cell, which you all should know about. So these reactions I just described right now is the acid-base buffer, is one of the acid-base buffer system of the blood, of which our red blood cell is an important contributor as a result of the cytoplasmic enzyme, which is carbonic anhydrase, that contribute to this reaction. Okay. So another function is transport of oxygen, which is so essential from the lungs to the tissue. Okay, so those are the major functional properties of red blood cells that you all should be aware about. So in this morphology section, we have been able to discuss about the size, the shape, okay, the concentrations of both the red blood cell itself, the concentration of let's look at what we have in the slide. The concentration of both the red blood cell, the concentration of the hemoglobin. Okay, so that has been discussed. So function of red blood cell, it transports hemoglobin, which carries oxygen from the lungs to the tissues, and prevent hemoglobin leakage through capillary membranes. Contains carbonic anhydrase, which catalyzes the reversible reaction between CO2 and water to form carbonic acid. So this has been explained. So in this very case, it acts as, so by an extension of this carbonic anhydrase action, it acts as an acid-base buffer due to the hemoglobin of the red blood cell. Though the shape and size has been discussed, at the thickest, the thickness at the thickest point, which is the periphery, is about 2.5 micrometer, and in the thinner center, the thinnest point in the center is about 1 micrometer or less. So the average volume, as said earlier, is about 90 to 95 cubic micrometer. So, and the shape being biconcave disc. Okay, this biconcave in form of a biconcave disc, it confers advantage, and the major or the chief advantage it confers on the red blood cell is that it provides the red blood cell the ability to change shape, to squeeze through capillaries without rupturing. And I told us that by the time you are comparing a mean diameter of about 7.8 micrometer with the mean diameter of a capillary, which could be as small as 3 micrometers in the capillaries of the spleen, so for a 7.8 micrometer diameter to pass through that tiny capillary, it means that the cells that is passing through has to squeeze, they have to squeeze their way through that capillary. So, and I told us that the enzymes in the red blood cell, the glucose, through the glucose transport on the red blood cell to form the ATP, provide the energy for the cell membrane. So all these things form they form the major powerhouse, or they give, they give pliability to the cell membrane. So by the time the red blood cell is becoming aged, is becoming old and weak, so due to what, depletion of the enzymes, due to depletion of energy. So anytime, so and they will become aged or weak after 120 days, which is approximately about 4 months. Okay, so after 120 days, so meaning that at this point the cell membrane will not be pliable again. The cell membrane will not really have enough, enough machinery to squeeze. So in this very regard, whenever they are passing through tiny capillaries, they start rupturing, especially the capillaries of the spleen, which is about 3 micrometer, they start rupturing, and that will lead us to the life cycle or the fate of red blood cells, which is going to be discussed later. Now, they also, in terms of concentration of red blood cell in the blood, so the amount is about 5.2 million per cubic millimeter. Okay, 5.2 million per cubic millimeter. So that is for the men. For the women, so 4.7 per cubic millimeter, of which it could either be plus or minus 300,000 Okay, so and when you do the calculation, so you are going to be having about, for the men, you are going to be having about 4.9 million to 5.5 million, while for the females, you are going to be having 4.4 million to 5 million. So, and I told us variation exists in terms of concentration, variation exists in terms of shape, variation exists in terms of size. I'm not going to go back to that. So we've talked on the quantity of hemoglobin, of quantity of red blood cells. So now quantity of hemoglobin which is inside the red blood cell. So the maximum it could be is about 34 grams per 100 milliliter of cells. So this has also been explained. So in the normal men we have about 15 gram per deciliter. Okay, 15 gram of hemoglobin per deciliter of 15 gram of hemoglobin per deciliter of blood, while in female 14 gram of hemoglobin per deciliter of or per deciliter of blood. Okay, so deciliter is more like 100 milliliter. Okay, 14 gram. Forgive my mistakes the other time. So I was saying 14 gram per milliliter. No, it is actually 14 grams of hemoglobin per 100 milliliter. Or so if you don't want to use 100 milliliter of blood, you can actually use deciliter. So 14 gram per deciliter of blood. And each gram of hemoglobin can carry about 1.34 mil of oxygen. So this should also be talked about. So concentration of the red blood cell, that's the first stage. Inside the red blood cell, there's hemoglobin. You talk on the concentration of the hemoglobin. Inside the hemoglobin, there's oxygen. You talk on the concentration of the oxygen. So and you talk on the variations that do exist between them.